So I will start. We will start today a new chapter which is chapter 13, which considers the kinetics of a particle. So first, in the previous chapter, we have considered kinematics of a particle, which involves the position, velocity, acceleration, and the relation with time and between each other. Now, in this chapter, we will focus on the relation between acceleration and forces. And always, don't do separation of chapters, because in one problem, you might need to combine several chapters. So, for example, you can from Newton law get the acceleration, and then once knowing the acceleration, you can use it to find position, velocity, etc. Okay, so the objectives of this chapter are to know how to work with Newton laws of motion, and to do the analysis of accelerated motion of a particle using the equation of motion. And as we have seen in the previous chapter, we have possible types of frames that we can work with. We can work in rectangular components. We can work in cylindrical coordinates. Uh, Also here, we can apply the Newton law or in Cartesian frame or in cylindrical components, or also in case of curvilinear motion, we can apply it in UNUT frame. Okay. So basically, if you understood well chapter 12, this will be easier for you. So to start with, a small reminder about the second law of Newton. The second law of Newton is the law that will relate forces to acceleration. So you have that sum of forces is equal, it's a vectorial relation. Sum of forces is equal to mass of a particle times its acceleration. Since it's a vectorial relation, we can decompose this relation into, depending in the case of it's 2D or 3D. So in 2D, it will give me two equations. Sum of x equals max, sum of y equals may. In 3D, it will give me three relations. Okay. Now, concerning the Newton's law of gravitational acceleration, it will give me the force between any two particles. So if you have any two particles, you will have a certain attraction between them. So, and by action reaction, the force of the first particle on the second one will be equal to the force of the second on the first. Okay, so same magnitude but opposite sense, same magnitude and direction, opposite sense. So this is the magnitude of it. It's the gravitational constant times m1 m2 over r squared. In general, this attraction force is negligible if the masses are not very high. Okay, it will become dominant when you have one of the two mass having a very high value. And one dominant example that we use a lot is which force? The weight, because the weight represents the attraction between what and what, between the earth and a particle. Okay, so if you apply this relation between the earth and any particle, then you will replace, let's say, m1 by mass of the earth. M2 will be the mass of the particle, here, let's say m, okay? And r will represent the distance between the center of the two particles. So here, of course, the earth will treat it as a rigid body if you want, but the center of mass of it is here. So the distance between the two centers is equal to the elevation, h, which is called also the altitude, plus the radius of the earth. Okay? So in this case, you will replace r by the radius of the earth plus h. In general, if we have small altitude compared to the radius of the earth, so if h is of orders of meters, then we can neglect it. And if h very small compared to radius of earth, we neglect it. And then what do we obtain? بيطلع لنا, if you calculate, look, if you calculate g times mass of the earth over radius of the earth square, you know what we will get?
بيطلع لنا small g.
Exactly. بيطلع لنا gravitational constant g. لأنه look in general نحن بنعرف إنه ال weight is g times m, small g times m. Okay, and this g will come from this relation. Now in case the altitude is very small, يعني you can neglect it compared to our Earth. In general you get g equal what? In your problems you use g equal to 10 or 9.81. Hey, the 9.81 is for negligible altitude, so you will use it in case of h very small compared to radius of Earth, and it will be equal to gme over re squared. This is what we use in problems. Now, if you have high altitudes, you can not say anymore that g is 9.81. Then you should calculate the new value of g by dividing by re plus h squared. Okay, and for satellite application, when h is very large, you can go to values of 0 for g, and because as you increase h, g will be reduced. Okay. Now, concerning the main difference for mass and weight, mass is a constant, while weight can be variable, okay, depending on the value of g. And the weight and mass are related through W equal to m times g. Another important difference, the mass is a scalar, while weight is a force, so it's a vector, okay? Now we will start with the Newton law. We know that the Newton law will relate forces applied on a particle to the acceleration of this particle. And in general, when we do sum of forces, we can replace sum of forces by one resultant force. Okay, this is called, if you draw the free body diagram, the free body diagram represent all forces acting on a particle. Okay, so when you draw the free body diagram, if you replace the summation of forces by one resultant force, okay, this resultant force is Fr is equal to the summation of forces. So the summation of forces is equal to vector Ma. Okay, the vector Ma represents the kinetic diagram. So if in a problem they tell you draw the free body diagram and the kinetic diagram, the free body diagram will represent all forces acting on the particle, all external forces, okay? And Ma will be, the kinetic diagram will just represent Ma, which is the resultant force, sum of forces. Now, of course, in case sum of forces is equal to 0, then you are in equilibrium. You can be in static equilibrium or you can be in dynamic equilibrium. Static equilibrium means that you are not moving. Dynamic equilibrium means that you are moving, but with constant velocity vector, so 0 acceleration. Okay? Any question until here?
دكتور بس فيك ترجع تعيدي آخر فكرة قلتيها؟
Yes, sure. Okay. About the equilibrium.
Yes, please.
Okay. For equilibrium, you can have static equilibrium or dynamic equilibrium. What is the difference? When I say static equilibrium, then my body is not moving at all. Okay? So the case of static, this is my particle, then V equals 0 and A equals 0. Okay? So it's not moving. This is called static equilibrium. On the other hand, I can have the scenario of 0 acceleration, but a velocity. I don't have 0 velocity. So if I have a particle, for example, moving on a straight line, but with a constant velocity, let's say, for example, V equal to 2. And not only the magnitude is constant, also there is a direction, and it should not change direction. Because if you have change in direction, this means that A is not 0. So here V vector, let's say, is equal to 2I. Then my particle is moving at a constant velocity vector. So it has a velocity, but of course, because this vector is constant, then its acceleration vector is 0. So this is dynamic equilibrium. Okay? And this is Vector A.
Yes, thank you.
Welcome. Okay. Now, concerning inertial and non-inertial frames, okay? When we talk about an inertial reference frame, it means that the frame, okay, is moving with constant velocity. If I want to say that a frame is an inertial frame, it means that acceleration of the particle is measured with respect to a reference frame that is either fixed or translates with a constant velocity. Because we will see together that if you have a frame having an acceleration, then you should add to the forces acting on the particle, you should add what is called inertial force of inertia. Okay? While if you have a fixed frame, or if you have a frame that is moving at constant velocity, if you apply in this frame the Newton law, sum of forces equal ma, okay, then you will just take into consideration the normal forces that we take into consideration. You should not add any additional force. Okay. On the other hand, let us see what will happen if we have an accelerating frame. And this type of frame is called or inertial frame or Newtonian frame. Okay. The other example is non-inertial frame. If I have a non-inertial frame, what will happen? For example, let's say you have a car that is accelerating. Okay, so I'll do a small scheme. You have a car, and this car is accelerating. So if you have, let's say, a person inside, and you feel it in general in your car, okay? If you are moving in a car, and suddenly you do a deceleration, what you will feel? If you decelerate suddenly, you will feel a force that will act on you. يعني هتجرب تكبكم لقدام. Okay, why? Because when I have an acceleration or deceleration in my frame, this will lead to a force of inertia that I will feel, okay, equal to minus my mass times the acceleration of the frame. Okay. And on the other hand, if you sit in a car and suddenly you accelerate, then you will feel a force that will push you backward. Okay, so the force that you will feel in a frame that is accelerating is always opposing the acceleration of your frame. This is why we say that if you are doing a Newton law in a non-inertial frame, so when you write sum of forces equals to, let's say this is a person P, then in general you apply sum of forces equal to MP times acceleration of P. Of course, with respect to a certain frame. If you apply it in the car, if you apply it in the frame of the car, what will be the acceleration of the person? In the frame of the car, the person is sitting on a chair, so it's fixed. So with respect to the car, the acceleration of the person is 0. Okay? But when I do sum of forces, I should consider, in addition to the normal forces, which are let's say the normal reaction of the chair, we should add to this, and the weight of the occupant. Okay? We should add to them the inertia force that is felt by the occupant. Okay, so here I will add, in addition to all forces, I should add the force of inertia, and the force of inertia is minus ma. And anyway, it's the mass of the person, okay, times the acceleration of what here? Acceleration of the car. Okay, and you will see that if I apply Newton law in the inertial or non-inertial frame, I will end up with the same relation. You know why? Because now, if I take the frame of the car, okay, let us say, what are the forces acting on the person? As we said, the weight, the normal, and maybe also the action of the chair. Let's say if the chair is doing a certain action on it in this direction, for example, I will call it F, let's say. Okay, now if I write, so here, if I write the relation in the frame of the car, what will be my equation? So in car frame, I will have F, which is, let's say, the friction between the occupant and the chair, plus normal reaction, and plus the weight. Okay, don't forget the inertia force, so minus m times acceleration of the car equals to, we said that the person is fixed relative to the car, so 0. Okay, so this is my vectorial relation in the frame of the car. Now if I want to write this relation in the frame, in the absolute frame, so if I am looking from outside, okay, and I want to determine the force of the Newton law on the occupant, then what I will write, so in fixed frame, I will write the following. First, since the fixed frame is an inertial frame, I don't add the inertia force. So I will have F plus N plus weight equals to mass of the person times, now I should multiply by which acceleration? By acceleration of the person. Okay, so it's m times acceleration of the person. But you know that since the person is fixed to the car, then the acceleration of the person and the acceleration of the car is the same. So it is m times acceleration of the car. So now if you compare the two relations, you will see that it is the same result. Okay, you will get the same equation, just in the first one MAC is to the other side, while in the fixed frame I will take it to the right side. Okay, so you can write your equation in any frame you want, but you should pay attention. If the frame is inertial, I should consider then in that case I should not put inertia force, while if I have non-inertial frame I should put the inertia. Okay, any question on this? Now in case the person was moving in the car, what will be the difference? If the person is moving in the car, then you if you work in the frame of the car, okay, then here you will put acceleration of the person relative to the car, okay, and here in the expression of the inertia you put minus m person times a of the car. So if you take this term to the other side of your equation, you will get mp times acceleration of the car plus acceleration of the person relative to the car. Okay, and what is acceleration of the car plus acceleration of the person relative to the car? It is هيدي equation relative acceleration. This will give you m person times acceleration of the person. So again, if you apply the relation into the inertial frame, you will directly obtain that F plus N plus W equal to the mass times the acceleration of the person. So both relations again will give you the same result. Okay? Any question on this? Okay. So let us continue. Now, concerning the equation of motion for a system of particles, you can have several particles acting on having motion in a system, okay? And if you decide to work on a system of particles, then you will say that sum of forces on these particles, okay, is equal to sum of mass of each particle times acceleration of each particle, okay? Now, when we talk about forces, you can say that we have what is called the external forces, which are it comes from parts that are not in the system, and internal forces are forces between the particles. But we will see together that this term will cancel out. Why? Because any two particles will have attraction forces between each other, okay? But by principle of action reaction, each two particles together will do opposite forces on each other. So the two forces will cancel out. So if we do the analysis 2 by 2, for each force we have an opposite for it. So when you sum the internal forces, which are the action reaction between particles, this term will be cancelled out. This is why when we apply the second law of Newton, we say sum of external forces equal to the mass times A. Okay? And here, this is the total mass. And this acceleration represents the acceleration of the center of mass. Why? Because as we have written here, summation of external forces is equal to summation of MIAI, yani the mass of each particle times the acceleration of each particle. But from mass, we know that the center of mass of a particle is characterized by what? Which relation? If I tell you how to find the center of mass of a system, this equation will allow me to find the position of the center of mass. The mass of the system times the position of the center of mass is summation of the mass of each particle or part times the position vector of this particle. And you know that if I derive this relation with respect to time, the first derivation will give me mass of the system times velocity of g, which is the center of mass, is equal to summation of mi vi. And if I derive again, so the second derivative will give me then the relation which I want, which is that the total mass times the acceleration of the center of mass is equal to sum of miai. Okay? So here, all I did is to derive twice this relation. This will tell me that I can replace sum of miai in the equation of Newton law for my system of particles. I can replace it by the total mass of my system times the acceleration of its center of mass. Okay? So Newton law, in summary, can be applied to a system of particles, and in this case, sum of forces will be equal to the total mass times the acceleration of the center of mass. Or also I can do it in parts. Yani I do summation of mass of each particle times, sometimes this is easier to do, times acceleration of each part. Okay? We will face systems and problems and you will see how to deal with. Now, as I said before, the Newton law is a vectorial relation and can be decomposed into components. It depends on which system I am working in. So first, the easiest system to start with is the rectangular coordinates, which we have seen in the previous chapter. So it's a fixed coordinates ijk. If I write the Newton law and I decompose it into ijk components, I can say that sum of forces can be written as sum of fxi plus sum of fyj plus sum of fzk, and it's equal to m times axi plus ayj plus azk. Now, if I put I components equal to each other, j components equal to each other, and z components equals to each other, I will get three relations. Sum of x equals max, sum of y equals may, and sum of z equals to maz. Okay? So, let us try to do, and of course, all relations I have derived in previous chapter will work. Okay? So after getting A, I can use the previous relations. So for example, if A is constant, I can use to find velocity and position, I can use V equal to V0 plus A constant times T. I can use that S is equal to S0 plus V0T plus half AT squared, etc. A small example on this. The 50-kilogram crate rests on a horizontal plane for which the coefficient of kinetic friction is mu k equals to 0.6. If the crate is subjected to a 400 Newton towing force, determine the velocity of the crate in 3 seconds starting from rest. So here I have a box, okay, and this box is moving on a horizontal plane. I want to determine what will be its velocity in 3 seconds. Okay, so whenever you know the final velocity and you have the time needed. Think about finding what is the acceleration. Because if I find the acceleration, I can deduce the value of velocity. And to find the acceleration, I will relate two forces. Okay? So the first step is to draw the free body diagram of my box. So I will ask myself, what are the forces acting on my box? I have first the normal reaction, I have the weight, and I have the force P. Okay? In addition, since they gave me the kinetic friction coefficient, then I have friction between the surface and the box. Now, I will explain in brief what is kinetic friction coefficient and what is static friction coefficient. Whenever you have two surfaces that are in contact, okay, when you try to move the object on the surface, you will have a certain, if the surface of course is not smooth, you will have a certain friction between the surface and the box. And this friction will not only be present in case of motion, even in case you have a static case, so your body is at rest, you can have friction. How? If you look at your figure here you are applying a certain force P. This force P has X component and Y component. The Y component will be opposed by what? You have the weight and you have the normal. So here, the P component plus the normal component will oppose the weight, okay? And the X component of P will try to move your crate. Now, the surface, the surface here, the floor will try to oppose motion of the box. So it will develop friction. Now, how to know if the friction is static or kinetic? Here, they already told me that the box is moving. So, of course, I can directly say, since my box is moving, it's a kinetic friction. Okay? But in case I am not sure, so if the problem given is different, if they give me both mu k and the mu s, and I should determine if it will move or not, okay? And in general, always mu s is higher than mu k. So for example, if they tell me that mu s is 0.5, then how to check if my box will move or not? What is mu s? Mu s is called the static coefficient of friction. And it means that the maximum possible static friction, okay? So if in case I have a static case, F static maximum can be computed by is equal to mu s times n. Okay? So it means that if I apply a horizontal force on the box smaller than mu s times n, my box will not move. The friction will be able to oppose motion. On the other hand, if I put a force P larger than mu Sn, then my box will move, and once my box is set into motion, the friction will not be any more static. The friction becomes kinetic friction. And the kinetic friction is equal to mu K. Okay? So here, let's say they didn't, I don't know if the block is moving or not. Okay? What should I do? I should first calculate what is F maximum, the static friction maximum, and compare it with Px to determine if motion will take place or not. Okay? So let us do it here. First step to get the friction is to calculate the normal reaction. To calculate the normal reaction here, what will I do? Which equation I will use?
Summation of vertical forces.
Very good. Summation of forces along y is equal to what here? Is my box moving along y?
No, it's equal to 0.
It's equal to 0. And how can I verify this from the normal? If I get a positive normal force, this means that the weight, okay, is over dominant over the P over P vertical, Py. So I will need also a normal reaction. In case I get N negative, this means that my assumption is wrong and the box will move upward, okay? Because if N is negative, this means that I lost contact. So just when N just becomes equal to 0, This means that I lost contact between the floor and the box. Okay, so to calculate n here, I do plus n minus the weight. So here my weight is 500, let's say, if we take g equal to 10, my weight is 500. So n minus 500 plus 40 sine 30, 400 sine 30, okay? 400 sine 30 is 200, equals to 0. So I deduce that n is equal to 300, okay? So now, since n is equal to 300 Newton, now I can calculate the value of the maximum possible static friction, okay? Fs maximum is calculated, so Fs max is equal to mu s times n. Since I gave you mu s equals 0.5 and n is 300, so the maximum possible static friction is 150, okay? So I can be sure now that my block cannot be in static case. Why? Because P is 400. So if you calculate Px, what is Px? Let me erase a little bit because it becomes messy. So Px is 400 cosine 30. Okay. So it's 200 radical 3. Okay. 200 radical of 3, which is larger than 150, which is the maximum possible static friction. So of course I am not in a static case. Okay. Now on the other hand, for example, if Px was 100, example, if Px is 100, then it is smaller than F maximum. So what will be the friction in this case? إذا كانت Px 100 شو حتكون الفريكشن force for equilibrium?
minus 100.
Exactly. It will be 100 in the opposite direction. So what I want to tell you إنه الstatic friction فيها تكون smaller or equal للميو اس ان. يعني كل ما how to know what is the value of Fs, I apply equilibrium condition, I get the static friction. كل ما زيد البي اكس حتضل تزيد static friction لحد ما توصل، يعني اذا بحط هون for example 130 بتصير الستاتيك كمان 130. اذا بوصل لل 150 يعني صرت على الليمت. يعني once I reached a force Px لما تصير Px 150 يعني if I increase it a little bit ما بقى عندي static case. Okay, so I can reach maximum Fs maximum equals to 150. 151 خلص صرت in motion, and once I am in motion my friction is not anymore given by this formula. I can ما بقى فيني اقول انه sum of x equals 0. فجيب الفريكشن kinetic. Kinetic friction is equal to mu k times n. يعني in this problem here, in this problem, the normal reaction was calculated to be 300. I multiply it by mu k, so 0.3 times n times 300. It will give me.
دكتور كيف عرفنا انه الاف اس ماكس هي 150؟
لانه انا اعطيتكم ميو كي equal 0.5. اوكي، الاف اس ماكس سوري ميو اس، الاف اس ماكس هي ميو اس تايمز ان. اتفقنا؟ احنا عملنا كالكوليشن قد ايه طلعت معنا ان؟ طلعت 300، وقلنا انه اذا ميو اس equal to 0.5 اوكي، شو حتكون الماكسيمم فريكشن، الماكسيمم ستاتيك فريكشن؟ حتكون 0.5 times 300 هي 150. اوكي، بس ما نحن عملنا بي اكس طلعت بي اكس اكبر من 150، يعني منه ستاتيك كيس، اجباري انه تمشي البلوك. اوكي، and in this case you have kinetic friction between the floor and the box, and the kinetic friction expression is given by mu k times n. فبتطلع هون 90. Okay.
Okay. Merci.
Welcome. So now I can draw the free body diagram on my box. I have a kinetic friction of 90 towards the left, 90 Newton. I have the weight. I have the normal. The weight already calculated, it's 500. النورمال جبناها من sum of y equals 0 طلعت 300. And px is p, we decompose it into two components. So now, since we have the free body diagram, we know all forces, then we are able to get A. No acceleration in y لأنه مثل ما قلنا sum of y equals to 0. Since py is not able to lift the box لأنه py أصغر من الweight. And then we only have motion in this direction, in x direction. And to get the acceleration along x, we will write that sum of forces along x is equal to mass times ax. The forces along x are plus 400 cosine 30 minus 90 equals to the mass, which is 50 times ax. Then we get the value of ax. Can we say here that ax is a constant?
Yes.
Of course, because all forces acting on our block are constant. So the force, of course, the acceleration will be constant. So we get the value and we say since ax is constant, then we can apply the relations of constant acceleration that we learned in the previous chapter. So to get the velocity, I can write just that v is equal to ax t plus v0. And since it's starting from rest, so v0 is 0, then v is just ax times the time. And here we are interested in the velocity in 3 seconds, so it's equal to 3ax. Okay, so here you can see the details of the solution. So first, I apply Newton laws in x and y. In y, the y relation will give me n at c. Here they used G9.81. This is why they got little bit different values, but it's fine. يعني نحن in general هول ما بنعتبرهم error يعني أو نحن بنقول لكم use G10 in general ما يكون في difference in values. Okay, and then when you replace NC by its expression in equation number 1, you will get the acceleration. A is 5.19 meter per second square. Now, since A is constant, we can apply the relation V equal V0 plus ACT, and we get the value of velocity. And here you can see the free body diagram and the kinetic diagram. So here, for example, you will be sure that sum of forces will be along x because no component of acceleration along y. Okay, ay is 0. يعني the kinetic diagram is restricted to a vector in x direction. So this is the free body diagram. This is the kinetic diagram. Any question on this? Okay, guys, happy Easter and hope to see you soon. Okay, well, good luck for the exams also.